Is this working? Fine? Perfect. Hi.
Hi.
How are you?
It's your day today.
It is actually, yes.
Very glad to have you here.
Oh, thank you very much. Yeah. I would like to first thank to the organizers for inviting me here. You have already seen some excellent lectures on the theory of matching. It's not going to be easy to talk after such great lectures. Instead of talking about the deep theory of matching, what I'm going to do is I'm going to focus on school choice, its theory, and empirical assessment of the markets and mechanisms. That's my goal. At least I can assure you one thing, it's only going to get better from now on. So now, what I'm going to do is I am going to introduce the school choice problem briefly. I am going to talk about some basic theory. And I'm also going to introduce some new theory here. And after that, I am going to give a theoretical comparison of the assignment mechanisms. And here, I'm going to emphasize that by the nature, the ordinal nature of the matching problems, we have so far been focusing on notions of ordinal efficiency. I am going to try to introduce a new perspective on efficiency for matching markets, and I'm going to apply this to school choice. So that is the plan. So what is school choice? School choice is a problem that my co-author and I started working on in late 1990s. By 1980s, before 1980s, traditionally, students were supposed to go to their neighborhood schools. In 1980s, Minnesota was the first school district that introduced some kind of choice over district schools. And from then on, the choice over public schools only grew. That map is from 2000. The red states indicate where there is statewide choice, and the yellow states indicate where there's some limited school choice by the time of 2000. If you want to draw a similar map today, it would be mostly monocolor graph. So there's choice almost everywhere. So then, what is choice? Choice is you live in a certain neighborhood. Your neighborhood offers you certain options about schools, but you are no longer supposed to go to your neighborhood school. You can choose from the schools that your school district offers. And there are many reasons for offering a choice plan. Probably one of the first reasons was segregation. If you rely on neighborhood-based assignment, what you see is neighborhoods are segregated along income and racial lines, and leaving minority and low-income students in neighborhoods with failing schools. That was probably one of the big reasons in 1980s. But today we have more reasons. One of the reasons is actually demand and supply issue, the basic demand and supply issue. How are we going to clear the market? The one size no longer fits all. When you look at school districts in the US and around the world, you are going to see that now the large high school movement that started in 1950s is being replaced by a small school movement. Schools are getting smaller and smaller. They are specializing on certain topics. Some of them on math and science, some of them on humanities, some of them arts. And in the past, you were able to select those courses in your large neighborhood school if you were living in an crowded urban district. But nowadays, those districts are actually offering bunch of options, not only about curricula but also about pedagogical approaches. Some schools focus on achievement in tests, standardized tests. Some schools focus on project-based training. Some schools focus on team-based training. So given this, there are also charter schools in the US. These are publicly funded but privately managed schools, alternative to the traditional schools. Given this variety of schools and a heterogeneity of student population, how are we going to clear the market? How are we going to meet the demand and supply? But it would be unreasonable to rely on a neighborhood-based assignment to clear the market in such instances. So a third equally important reason is probably creating market competition among schools via choice. Public schools are free of charge in most places. You are not supposed to pay for your education. If there's when we do not have money, when teachers are paid equally across the district, how are we going to create competition among schools? And choice is seen as one of the instruments to create that. Now, given that, what is a school choice problem? A school choice problem is a matching problem. On one side of the market, we have students. On the other side, schools. Students rank schools in a preference order. Student 1 prefers school 2 to school 1, school 1 to school 3. Schools may also rank students. I will call them priorities, but they may also reflect school preferences. In this case, school 1 ranks student 1 the highest, then 3, then 2. And where do these priorities come from? Well, most of the time, these are given exogenously. For example, in the old days in the Boston public schools, the priorities were determined by whether a student has a sibling that is attending a school, or if a student lives within a walk zone of a school. And the highest priority would go to the students who have a sibling and who live within the walk zone. The next highest priority would go to the students with only siblings attending the school, and so on. And these are actually thick classes. There are many students in this priority group, many students here and many students here. Ties would be broken by a lottery among each class. So now, what are the policy issues? There are some of them are trivial. Feasibility. One of them is, and in this example, I'm going to use this example again and again. In this example, there is only one seat at each school. Probably the first one is feasibility. We do not want to overcrowd schools, so the number of students assigned to schools is not going to exceed the available seats at any school, and only eligible students are going to be assigned, enrolled at each school. The second one is individual rationality. No student is going to be forced to attend a school, or she's going to be assigned a school that she does not prefer. Now,
a student cannot go to school?
well, they may have outside options, and one of the outside options might be a neighborhood school, and we could actually expand this preference list by assuming that.
But that's
Yeah.
a serious option.
Yeah.
It's not a residual. Let me ask you, is there any reason to suppose that student preferences, presumably the objective is to school the children, not to satisfy their preferences.
Mm-hmm.
And the reason I'm saying it is, this is one of the cases where you assume consumers are uninformed. That's, after all, they're going to school, which means they know less, and even their parents probably know less about the school than in principle the public does. So why should we respect student preferences?
That's actually a good question. That
As I may say, that child is better off going, you know, being put in a school which is somewhat above his level in order to stimulate him or something. Or, you know. Why should children sort of the family preference seem to be considered? This is one example where they're ill-informed.
Exactly.
And they know they're ill-informed. They might prefer to have somebody else make
that is true. That's true. first obvious answer to this question is, of course, consumers. The students are seen as consumers in the U.S. market, and
This is one place.
that's one. Yeah, but on the other hand, in New York, for example, certain schools are specialized in educating certain types of kids. For example, low-achieving kids. Some schools focus on low-achieving kids. So if they are successful in educating that subpopulation, why should we respect the preferences of families for? This is a policy question that we need more empirical evidence for. But I am going to take the consumer point of view, and in the second lecture, I'm going to introduce some more evidence towards that. And probably the third obvious criterion is incentives. Do students submit preferences truthfully? And that is not as obvious. In the old days, Boston used to assign as many kids as possible to their first choices. And after those first choice assignments were made, it tried to assign as many kids as possible to their second choice and so on. And where there are more students who rank a school than available seats, the ties would be broken by the priorities. Priorities would be used to ration the seats at schools. So what would happen in this case? In this case, remember there's only one seat at each school. Student 2 is going to apply to school 2. And he's going to get the seat. 2 and 3 are going to apply to S1. S1, it has only one seat, but it ranks 3 higher than 2. So 3 is going to get S1. And 2 now, when she applies to school S2, it's already gone. And she's going to get S3. That is going to be the old Boston matching. What 2 could do is actually, by ranking S1 as her first choice, she's actually giving up her priority at school 2. She's the highest ranked student. If she actually ranked S2 as her first choice, in the first round, 1 and 2 would be considered for the seat at S2. And since she has the highest priority, she would get the seat. And she would actually benefit from that. That's not something that actually we fancy about, we economists fancy about. That is something that was advertised in the public school guide by the district itself. For a better choice of your first choice school, consider choosing less popular schools. Not only that, we actually became aware of some mailing lists, and in those mailing lists, experienced parents were actually training newcomers about how to strategize, how to rank schools. So, given that, the next question is what to do with priorities. Why do we have those priorities there? This is the one that's going to determine whether the market is a one-sided or two-sided matching, and we are going to see some applications of that. And probably putting Professor Arrow's question aside, probably one of the concerns that we have is student welfare. We want to maximize student welfare given preferences. This matching, for example, ETA matching, assigns student 1 and 2 to their first choices, and 3 to his last choice, and that is a Pareto efficient matching. The problem with that is student 3 prefers S1 to S3, but S1 goes to student 2 who has a lower priority than 3. That is what we call a blocking pair. If we want to avoid such blocking pairs, we end up with the stable matchings. So if that's all we want, we already know what we can do. And here is a very quick overview, and an extended treatment of this literature is available in previous lectures. The first thing is we know that stable matchings exist under certain conditions. In our case, the market is already two-sided. But no complementarities among students is going to be important for the existence of stable matchings. There may be multiple stable matchings, and the set of stable matchings forms a distributive lattice. That means we can pick a stable matching that is best for the students among all the stable matchings. We know that no stable mechanism is incentive compatible for all agents. If schools are strategic agents, as well as students, we would not be able to find a mechanism that's incentive compatible for all agents. However, the Gale-Shapley's student proposing deferred acceptance algorithm is incentive compatible for students. And actually, in general, in a many-to-one matching, we do not have incentive compatible mechanisms for schools who match with many students. So that after that, then, that only gives us a nice solution. Applying a Gale-Shapley's deferred acceptance algorithm, we get the best stable matching for students. Also, it is incentive compatible for students. The problem, well, a potential problem with that is, if you look at the Gale-Shapley matching, student 1 is matched with S1, student 2 is matched with S2. They are both getting their second choices. They would be better off if they exchanged their schools. The reason that actually this matching, Gale-Shapley, is Pareto dominated by this efficient matching, where student 1 and 2 get their first choices.
Pareto dominated means only respecting student preference.
Correct, yes, exactly.
If the school priorities mean anything,
sometimes they will.
They should have some weight.
Yeah.
I don't know what they mean.
Yeah.
I understand why they prefer the students, but the school priorities mean something. I don't know what.
Exactly.
In the welfare sense.
When they mean something, actually, and that was one of the reasons why New York City Department of Education decided to adopt a stable matching. When it means something, something, if it reflects school preferences, then we already have a reasonable solution for that. But it still does not address your first question. Now, given that, then, the reason that those two cannot get their first choices under Gale-Shapley is because student 3 would be blocking student 2 at school 1. So, if we ignore stability, if we ignore, that's not what I am promoting, but if we want to ignore school priorities or school preferences, and if we want to optimize student welfare, do we have efficient matchings? The answer is yes. By finiteness, we are going to be able to find Pareto efficient matchings with respect to student preferences. And actually, there is a simple mechanism for that. Order the students in put the students in an order, and one at a time, given this order, each student is assigned his most preferred option among the available schools. That is going to give us efficient matching. Actually, the set of efficient matchings can be found by changing the order of students. This mechanism is incentive compatible for students. And there are some nice characterization results. One of them that I want to highlight is the following. If we want Pareto efficiency with respect to student preferences, if we want group incentive compatibility, that is, there's not going to be any subgroup of students, coalitions, who are going to be able to manipulate the system. And if you don't want no manipulation via reallocation, what does this mean? This means I missupport my preferences, you missupport your preferences, we get an assignment, and then we exchange our assignments. I go to your assigned school, you go to my assigned school. And we become both better off. If we do not want that kind of manipulation, that actually characterizes an exchange mechanism. And I'm going to talk about this in a moment. Now, so let's talk about an efficient solution on this example again. Now, let's completely ignore priorities. If we ignore priorities, we know a serial dictatorship would allocate schools efficiently. But then, why do we have priorities at the first step? Well, one way, it's really about interpretation. One way of interpreting priorities is they may actually determine the initial assignment. In this example, student 1 might get a seat at school 1, and student 2 might get a seat at school 2, and another seat at school 3. That initial assignment might not be efficient. If it is not efficient, we can actually look at, create an exchange market and find an efficient outcome in that exchange market via Gale's top trading cycles algorithm. That is what we proposed in our original article. And here is how the top trading cycles mechanism, an efficient mechanism, works in this case. Each school is going to point to the student that it ranks highest. S1 is going to point to student 1, S2 is going to point to student 2, and S3 is going to point to student 2 as well. And each student is going to point to his or her most preferred school. 1 is going to point to S2, and 2 is going to point to S1, and 3 is going to point to S1. And we are going to find a cycle, and we are going to complete the trade along this cycle. 1 is assigned 2, student 2 is assigned S1. In a way, those students are actually exchanging their priorities. That once we perform this trade, we have a reduced economy. In that reduced economy, we find another cycle, and we end up with this top trading cycles allocation where student 1 and 2 get their first choices, and 3 ends up with her last choice. Incidentally, this matching, Pareto dominates the Gale-Shapley matching in this example. Now, that mechanism is Pareto efficient and incentive compatible. And so these are the two major assignment mechanisms that we talk about when we talk to the school districts. So what happened then? The early applications actually tell us a lot about how the market design work for school choice has evolved. The Boston public schools, the parental incentives to navigate the Boston system were brought to light by our article, and that actually initiated the debate. And after that, only after that, the Boston public schools decided to change their admissions system. Well, the schools were under the full control of Boston public schools. Therefore, stability was not a major concern for them. Those priorities are exogenously determined in Boston, and violating those priorities was not a major concern. Actually, a task force initially recommended top trading cycles, which violates priorities, but eventually the Boston public schools adopted Gale-Shapley. Yes.
I want to stop you for a moment. You're a bit running for me.
Uh-huh.
I want to understand why serial dictatorship works while the initial policy of letting students choose their first choice, and then giving them all the first choices, and then go to second choice, etc. Why the second one didn't work? So what is
the second one? Is what?
So
the first one is serial dictatorship.
One is serial dictatorship. You say it works, and you say in serial dictatorship you let people choose their first priority and then go to second, etc. Now you started your lecture by talking about a similar method where students were choosing the first choice, etc., and then it didn't work. It was manipulable, right?
That's correct.
So
yes.
what was exactly? Can you give intuition?
Yeah. Yep. So that's a good question. So the question is serial dictatorship in which students choose in a given order is incentive compatible, but the old Boston mechanism in which students also kind of choose in an order does not work. The reason is the Boston mechanism uses priorities to break ties, and serial dictatorship does not. So if I have a popular, if my first choice is popular, and if my second choice is also popular, but if I have a higher chance of getting into my second choice because of my high priorities at my second choice, if I do not rank that school as my first choice, I am actually giving up my priority at that school. And I am risking it.
Serial dictatorship, now everyone fights, let's say, for popular school. Who will make the choice?
In serial dictatorship, priorities do not play a role. Only preferences play. So if I am the second or third person, doesn't matter, as long as I am always going to choose the best option among all the available options.
But then I guess that the order matters, right?
Yeah, the order matters,
So
exactly.
you cannot. So you have a problem. Who will be the first one to choose?
Correct, yes. And most of the time you actually use a random lottery to determine this priority. Exactly. And actually, the New York State choice system uses a serial dictatorship mechanism for part of their assignment. Now, so the reason for the Boston Public Schools to use Gale-Shapley was actually they expected that Gale-Shapley would assign students closer to their homes, although our simulations did not reveal much difference in terms of distance between home and assignment of students. Now, New York State is a different story. It had a centralized but uncoordinated multi-offer admissions system in place. But that system was not able to clear the market. About more than 30,000 students out of about 90 students were not being matched to any of their choices by the end of March, by the end of the main admissions process. And being aware of AL's work for the National Residency Matching Program, the city contacted AL in 2003. Then we consulted them with the design, and the major difference between New York and Boston was, in New York City, some schools are strategic agents. They actually express preferences over students. And some schools were reported to conceal capacity in order to be able to enroll students out of the centralized match. Given these concerns, New York City was actually a two-sided matching, and that is why the choice was kind of obvious in New York City. So one further difference between Boston and New York, Boston was the first school district, probably maybe in the so Boston actually, the Boston example is probably the first example in the literature that uses strategic proofness as a public policy concern related to transparency, fairness, and equal access to public facilities. In contrast, in New York State, it was the school incentives, in addition to student incentives, that dictated the Gale-Shapley algorithm. Now, what's going on? Yep.
How much the school's preferences are dispersed? Like how different the school preferences are?
They are actually quite different, because in Boston, for example,
And in New York.
New York is there are about 700 plus programs, and there are about 5 different admissions policies, and some schools are completely allocated randomly. Some schools give priority to students in their borough. Some schools give priority to students who visit their information fair or visit the schools. So there's quite a lot of variety.
Or these all public information?
This is all public information, yes. And that's actually going to have consequences on welfare. And we are going to come back to that. And at that point, I'm going to emphasize the difference between New York and Boston briefly as well. So what's going on? San Francisco is the first district that adopted top trading cycles. And DC, Denver, New York all switched to Gale-Shapley. And New Orleans initially started with top trading cycles and then switched to Gale-Shapley. There's a nice contrast between Denver and New Orleans. These two districts have a big number of charter schools. Charter schools, in Denver, charter schools can run their own admissions processes. Therefore, participation of charter schools in the centralized admissions was a big issue. That is where school preferences get into the picture. In order to meet school preferences, Gale-Shapley was the kind of choice, because we already know from Kegel and Roth that if a market is two-sided, mechanisms that are not stable or hard to survive. And in New Orleans, on the other hand, most of the charters were are controlled by the recovery school district. That is why participation is not a big issue, and that's why they were able to use a Pareto efficient matching mechanism there. In the second year, they incorporated some state schools into their admission system, and the admissions to those state schools are regulated by laws, which actually, and those regulations impose the stability constraint on the matching problem. That's why they switched to Gary Shapley in the second year. So here's some new theory. Here's the question that I would like to address first. There are many strategic proof and efficient mechanisms. Why that particular top-trading cycles mechanism? In that particular top-trading cycles mechanism, remember, every school points to the highest ranked student, and every student points to his or her most preferred school. And we find a cycle. Along this cycle, we assign the students. In a way, students actually exchange their priorities. So why that top-trading cycles? There are so many strategic proof and efficient mechanisms. One of them is randomly rank students and let them choose one at a time, ignoring all the priorities. So there's actually not much result on that in the literature. Well, one observation comes from the house exchange markets. If actually think of school choice as a housing market. Suppose students are initially assigned their neighborhood schools, but they want to transfer. That's each student owns a seat at their neighborhood schools. Now we have an exchange market. In that exchange market, actually, there is a unique Pareto efficient and individual rational mechanism. That's also strategy proof. That is top trading cycles. And that top trading cycles, every student is ranked highest at his or her initial neighborhood assignment. But that is not really this situation in school choice. I may get a neighborhood priority at one school, I may get a sibling priority at another school, and there may be so many students who are ranked with me, above me, below me. And why do I use that priority? Well, another one may be in a one-to-one market where each school admits can enroll at most one student. We have this nice characterization result. If we want Pareto efficiency, if we want group incentive compatibility and no manipulation via reallocation, then there must exist some kind of priority structure, which Popeye calls an ownership structure. And under that ownership structure, students exchange their priorities and they find an efficient allocation. But that result still does not tell us why we should use that particular priority structure. So what I will do next is this is a joint work with Yanku Che, Olivier Torso, and Alot and Parag Patak. And what I'll do is I'll give a definition. I'll say two mechanisms, phi and phi prime. I'm going to say that phi produces less NV than phi prime if and only if whenever a student and school pair blocks phi, it also blocks phi prime. So there is more blocking pairs under this mechanism, under every preference profile. Yes?
How could you justify to let them students to exchange their priorities, because priorities are given in some like educational purpose or some philosophy that the school districts want to let the students allocate according to some reason.
That's exactly the open question. That's exactly what I'm trying to address here. I mean, after all, it's a policy question, but do we have a normative justification for the trading of priorities? There's not much result for that, and this is where I am heading towards now. Now, this is actually originally, this result was obtained by Olivier Terceau originally, which was based on an earlier result by us. And here is the result. There is no strategic proof and Pareto efficient mechanism that produces less NV than top trading cycles mechanism, given the priorities. So if we have a priority structure set in place, which might be given exogenously, sibling priorities, neighborhood priorities, given those priorities, we want to achieve Pareto efficiency and strategic proofness, but not any Pareto efficient allocation. We want to achieve the one that produces as little blocking pairs as possible. Yes?
So less envy is not a complete order.
It is not, correct.
And so there may be many other mechanisms in principle that could be maximally envy-free.
Correct.
You have a characterization of them?
Not yet. Even for this simple case, I'm going to talk about it in a moment. When I relax this last assumption, even then I do not have a characterization, and I'm going to mention about it. That's a good point, actually. Now, what's the proof? Here's the sketch of the proof. Yes. I need to clarify this. When I say Pareto efficiency, I usually mean with respect to student preferences.
Okay, so when it's still sharply, it's student optimal and it's also strategic proof, so why is it not?
It is student optimal within the set of stable matchings, but it is not fully Pareto optimal. So there may be matchings that Pareto dominate to give sharply outcome, but they are not stable. So let's start with a mechanism, phi, which is Pareto efficient, strategic proof, and actually it produces less NV than top trading cycles. And here is the market, and this is just an illustrative example. Suppose this is the first cycle created under top trading cycles, and let's suppose that, and then in that cycle, school 1 points to student 1, student 1 points to school 2, and so on. Student k minus 2 points to school k minus 1, school k minus 1 points to school student k minus 1, and so on. What does this mean? This means, for example, this student, since he is pointing sk, it must be the case that he ranks sk as his first choice. And he might be ranking sk minus 1 somewhere here, which might be acceptable for him or not, doesn't matter. But we know that actually this school ranks that student the highest in the priority order. Okay? So let's suppose that these two mechanisms are not actually equal. And let's suppose that that student's assignment on the top trading cycles is going to be S1. Let's suppose that he does not get S1 under phi. So here's what I'm going to do. I am going to move sk to the bottom of S1. S1 is this student's first choice because he's pointing to that school under top trading cycles, right? So by strategic proofness then, since the phi mechanism is strategic proof, that student is not going to be assigned his first choice under this new preferences, because otherwise he would be able to manipulate the phi mechanism. We know that he is not assigned his first choice under the original preferences, so he should not be assigned his first choice under this alternative. So he's not going to be assigned S1. And we know that top trading cycles is going to continue to assign this student to S1. Therefore, it must be the case that that student must be assigned SK. Otherwise, if that student does not get S1 and he does not get SK, he would be blocking some other student at SK. Why? Because he is the highest ranked student here. But we know that that cannot happen. Why? Because this student is not blocking anybody on the top trading cycles, and phi produces less NV than top trading cycles. in order to avoid that blocking, we must, phi makes sure that student IK actually gets school SK. But if this school is gone to IK, that student is not going to be able to get this because there's only one slot, right? So let me do the same trick here. Let me now move that school SK minus 1 just to the bottom of SK. Remember, at that school, IK minus 1 has the highest priority. A similar argument is going to prove us that student IK minus 1 is actually matched by phi to the school that he's ranked highest. And I'm going to do this for all students in that cycle. And then I can show that every student is going to be assigned the school that points to him. But these are the second choices. These are the second choices in every student's choice list. They could be made better off if they actually exchange those schools. And that creates a contradiction, because we know that phi is efficient. And therefore, there's not going to be any strategy proof and Pareto efficient mechanism that actually produces less NV than top trading cycles. Top trading cycles is going to create some blocking pairs, but there's going to be no one that's going to create a smaller number of pairs. But that goes back to your question. What do we mean by smaller? I have given a particular definition of smaller. And let me stick to it, and let me relax one assumption in my characterization result. It is, suppose S2 has 2 slots, and S1 has 1 slot. The top trading cycles is going to give those 2 students their first choices. And this student is going to get S2. But there's actually another matching here, where student, instead of student 2, student 3 is going to get S1. And that's actually going to be completely NV free. That is Pareto efficient, and it's NV free. And actually, based on that example, we can create, when some schools have more than one seat, we can create strategy proof and Pareto efficient mechanisms that actually produce less NV than top trading cycles. So what is our conjecture? Something that we are still working on. I think finding a strategy proof and Pareto efficient mechanism with minimum NV is computationally hard when there is more than one seat at schools, at some schools. So the short answer to your question, we haven't worked out the alternative definitions yet, because we haven't worked out that definition yet. Now, what about that? So this is a simple characterization of top trading cycles. How do mechanisms compare? In that lecture, I'm going to give you some theoretical comparisons, and in the next lecture afternoon, I am going to talk about some empirical comparison of those mechanisms. Now, we know that Gale-Shapley is stable but not efficient, Pareto efficient, with respect to student preferences, and top trading cycles is Pareto efficient but not stable. And in our examples, we had this simple example. We had this Pareto domination result, but that result actually does not hold in general. There is no Pareto domination between those two mechanisms. Here is an example where Gale-Shapley assigns student 2 to his second choice, and the top trading cycles assigns student 2 to his first choice, and vice versa for student 2. There is no Pareto domination relationship between those two matchings. So how about the Boston mechanism, the one that was replaced by Gale-Shapley? We know that it is not stable, but it is also not strategy proof, which means parents are going to play a game, information revelation game. And in the complete information game, the Nash equilibrium outcome of the Boston mechanism is stable with respect to the true preferences. And therefore, we don't know which equilibrium parents are going to be playing. But if they can coordinate on a Nash equilibrium, we know that that equilibrium is not going to be better than the Gale-Shapley outcome. So in a recap then, here's how we have been proceeding about Boston versus Gary-Shapley. The Boston mechanism is manipulable. If you rank a school higher, you actually improve your odds of getting into it. So this creates some incentives to manipulate the system. It produces a stable matching in every Nash equilibrium. Therefore, but it does not guarantee that it's going to produce the student optimal stable matching. Deferred acceptance, on the other hand, it is strategy proof. Dominant strategy incentive compatible for every student. And it actually picks the student optimal stable matching. And that, therefore, there is a sense where a switch from Boston to deferred acceptance actually improves student welfare unambiguously. Now, these arguments hold under the assumption that schools have actually strict priorities. In reality, schools have close priority groups. There may be many students in that group, many students here, many students here, and many students here. Now, within each group, ties are broken randomly. And I'm going to show that actually that random tie breaking is going to have significant welfare consequences. And actually, although strategy proofness justifies the choice of deferred acceptance over Boston, rejecting Boston on the basis of efficiency might be misleading. Yes?
So could you say a bit about where these school priorities come from? Because they seem to be essentially reflecting students' preferences. That is, a student's family is going to benefit if they send their kids to the same school, less transport. They're going to benefit if they don't have to walk so far. So why do we call these school priorities?
Actually, it really depends. Schools might be ranking students in preference orders, but in most cases, in Boston, for example, these priorities actually reflect the choices of the society over assignment. So in this case, one might argue that assigning siblings together would create positive externalities or spillovers among siblings, or it would solve the coordination problem for parents. It would be easier for them to...
But that's a parent's
Yeah, yeah,
consideration.
exactly.
If parents are already expressing their choices, why does this have to be in the school priority? Parents can express it unless you want to impose paternalism.
Let's simplify the problem. Let's consider a school district where there are no priorities. As a parent, I want to send my kids to the same school. I could express this preference in my choice list. My elder kid is going to school A. I might rank school A as my first choice for my younger kid. For me, just ranking that school as first choice is not gonna, it's gonna improve my chance of getting into that school. But if I also have sibling priorities at that school, that would further improve my chances of putting my younger kid into the same school. So these are actually kind of designed by school districts, and they actually reflect preferences of the school district and families on how assignments should be made.
So it's a way that schools can ensure that parents, particular kinds of parent preferences, get embodied.
Yeah, exactly.
And then another question is how you could regard the priorities, the goods to be traded. Shouldn't the priorities are given to a student when only if the students are going to that school? Because the priorities are given that way. So how you could, again, justify trading? So why priorities are given by some affirmative action? Can you still say they can trade their priorities by top trading something?
That's a good question. For example, let's apply it to sibling priorities. Yeah. There is a nice justification for sibling priorities. Parents would have an easier time to take their kids to the schools if their kids are assigned together.
Right.
Right? So, but if I get a sibling priority at a school, and if I have no intention of sending my younger kid to that school, why should I be allowed to exchange my priority at that school for another school? That's a good question. So that top training cycles allows for that. Gale-Shapley does that. So as economists, we do not actually state a preference over one mechanism versus another. The approach we take is try to understand what the districts are trying to implement, and can we write their problem in normative ways. And given those normative criteria, what is the best matching mechanism available?
Do you have any intention how the school district policymakers think the priorities?
Well, during one of the parent district meetings in Boston back in 2004, I believe, one of the questions that Al asked was, for example, parents were discussing heavily about the Volkswagen priority. One argument is, I buy an expensive home to send my kid to a school in that neighborhood. Why should somebody else come and take that seat and not my kid? Right? One of the questions that Al asked to answer another parent's question was, how do you feel if your kid does not go to your neighborhood school, but somebody else from outside of your neighborhood gets and takes it? That's not something that we should decide as market designers. This is something that the society and the district should decide. So, what do I mean by that? I mean, strategy proofness is really, yes.
That someone loses from getting that priority.
What's that?
Might it be that the student loses because of that priority, so it prefers not to get a priority in some mechanisms?
In some mechanisms, yes, but in Gale-Shapley, for example, no. If you get higher priority, you get a better chance of getting into better schools. Yeah, that's actually Balinsky and Sönmez's characterization of Gale-Shapley. Now, strategy proofness, yes.
Just a little curious about how strong is the sibling priority. Like if a family has multiple children, they have higher chances for all these children to go to better schools. Would that affect their decisions or adopting more children?
Yeah, that actually introduces some manipulation possibilities. Actually, some parents try to get their older kids earlier into a school at a pre-garden PK grade. If they can get their elder kids into the school, they could actually they can gain sibling priority for their younger kids. That actually happens. But the school choice problem is definitely much bigger than the one that I described. And there are strategic opportunities outside of that model for students and schools. And let me just stick to that simple model for the time being. Strategy proofness is important because it actually reveals important demand data about schools, which you can use to design your school districts. And that's what I'm going to talk about later in the afternoon. But rejecting one mechanism based on an ordinal efficiency criteria might be misleading. And that's what I'm going to talk about. I'm going to talk about ex post versus ex ante welfare in matching. So what do I mean by that? Remember, there is randomization in tie breaking in the school assignment mechanisms. And that actually creates lotteries for students. And here's a simple example. There are 3 students, 1 to 3, and 3 schools, 1 to 3, each with 1 seat. And let's suppose that there is no priorities. Let's assume that the deferred acceptance algorithm is going to assign a single lottery number to each student. And students are going to be ranked at schools according to that single lottery number. So deferred acceptance is strategy proof, right? And in this particular case, each student likes S1 the most, then S2, then S3. So since it's strategy proof, everybody is going to submit their preferences truthfully. Everybody is going to rank S1 as first, S2 as second, S3 as third. And since the assignment is random, each student is going to get each school with probability 1/3. So what is the expected utility now? The expected utility, student 1 and 2 are going to get school 1 with probability 1/3. School 2 with probability 1/3, and school 3 with probability 1/3. That's going to give them an expected utility of 1/3. And student 3, likewise, is going to get an expected utility of 1/3 from an ex ante point of view. Right? What does Boston do? If instead of running deferred acceptance, if we run the Boston mechanism, what would it do? Now look at student 1 and 2. Their second option is almost as bad as their last choice. Right? They would do everything to get into their first choice. For student 3, there is a nice second option here. Knowing that those students are going to compete for school 1, he might actually opt out for school 2. How are they going to compete for school 1? They are going to rank that school as their first choice. And student 3, he could rank school 2 as her first choice. If he does that, he will guarantee a seat here. Because remember, in Boston, schools are assigned by choice. If she ranks that as first choice, and if she's the only one that's ranking that school as first choice, she's going to get it. And actually, in the unique equilibrium of the complete information equilibrium of this game, student 1 and 2 are going to rank S1 as their first choice, and student 3 is going to rank S2 as her first choice. So student 1 and 2 are going to compete for that school, and student 3 is going to get that school for sure. Her expected utility is going to be 0.4, and the expected utility of those students are going to be 0.4, which are actually all higher than 1/3. So the Boston mechanism is actually creating higher expected utility for the parents, for the students. Yes.
Yeah, just a clarification question. When you talk about deferred acceptance with lotteries, the lotteries are performed each stage of the mechanism. So the first stage, both of us chose the same school. The school has no priorities. So in the first stage, there is a lottery. Then the second stage, I compete with Eyal. There is another lottery, right?
You could do it this way. You could do it this way. But the way I imagine is, let's just run a single lottery at the outset. You get a number, I get a number, Eyal gets a number. And each school ranks us according to our lottery numbers. For example, if you get the best...
Because the school has no priority,
Yeah.
you
Yeah.
assume that the ranking of the school is according to
Yeah.
priority.
Yeah, exactly. Now, you might think again that we economists are fancying about this, but I am fascinated by the intuition of parents, actually. Here is, this is from the recordings from a parent meeting that we attended in Boston back in 2004. I am troubled that you are considering a system that takes away the little power that parents have to prioritize. What do you call this strategizing? As if strategizing is a dirty word. And here's another parent 1 year later. If I understand the impact of Gail Shapley, and I have tried to study it, and I have met with the Boston Public School staff, I understood that, in fact, the random number has preference over your choices. Now, this is the intuition that the layman intuition that the parents have, and we have formalized that in one of our work. Matching problems are actually difficult to work with when you incorporate cardinal preferences. So in order to have some reasonable analytical results, we need to make a lot of assumptions. And these are the assumptions in a simple model. Finitely many students and schools. Schools have no priorities. Students share the same ordinal preferences. That's why there's one good school that everybody likes, another one with a very good science education. Everyone likes that school as their second choice. But the cardinal evaluation of schools differs. Although I like school 1 most, maybe I don't like it as much as you do because it's a little bit farther away from my home. Let's assume that those cardinal evaluations are actually drawn independently from a commonly known distribution. Each student knows his or her own valuation, but cannot observe the others. So in any symmetric Bayesian equilibrium, we can show that actually each type of student, I, gets a weakly better expected utility under the Boston mechanism in comparison to his expected utility under Gale-Shapley. Now, there's also a sense, yes? That actually corresponds to random field dictatorship. Yes, that's a good point. Yeah. Now, there's also a sense that actually the Boston mechanism might improve access to good schools for students who do not have priority at those schools. Now, neighborhood priority is a common feature in many school districts. For example, in Boston, an elementary school student gets neighborhood priority if he lives within 1 mile radius of the school, and similarly for middle and high schools. And a major goal of school choice is actually to provide equal access to good schools, but the neighborhood priority compromises that goal. So how do mechanisms perform in terms of access to good schools? We can actually show that if we add neighborhood priority to our simple model, we can show that every student without priority at one of those top 2 best schools can actually have a strategy that guarantees a strictly higher probability of getting into that school, into one of those schools, under the Boston mechanism. That's in comparison to deferred acceptance. Why? Because deferred acceptance, regardless of what your priorities are, what your underlying cardinal valuations are, you always tell the truth. And actually, you do not risk anything by doing that. So if your neighborhood school is not your first choice, you can still rank it as your third choice. And you are not going to compromise. You are not going to give up your priority at your neighborhood school. That is why actually Boston, there's a sense that Boston might give more access to good schools for students who do not have priorities at those schools. Now, let me skip these 2 slides, given the time limit. Let me then raise the following question. So, first we argued that Gale-Shapley is better than Boston because it's strategic proof. Now, are we arguing that the Boston is better, so we should go back? Not really. Actually, what is lacking in Gale-Shapley is a strategic instrument that would allow students to pass their cardinal preference information to the mechanism. Yes?
Formally speaking, couldn't you do that by making the choices lotteries? So the objects of choice would be lotteries over schools, and then you have ordinal preferences over lotteries.
Correct. Correct.
And then you could use Gale-Shapley for that.
Correct. Yes. Yeah. Yeah. That's true.
I'm not saying it's practical, but you could.
Yeah.
Formally, you could do it.
But the practical thing, I'm going to emphasize that practical thing. I'm going to offer an alternative mechanism, which is going to be practical, which is not going to be the most general formulation of the mechanism design problem we have in hand. But our concern is, can we design practical, simple mechanisms that actually is going to introduce some kind of instrument that's going to help parents pass some of their cardinal information to the mechanism. Yes. Now, so the Gale-Shapley does not pass any information about cardinal information. Why? Regardless of what your cardinal information is, you will always submit the same ordinal ranking. It is your dominant strategy to do so. Now, and the priorities are used as a rationing device in school choice. And when priorities are caused, we usually randomize in Gale-Shapley. But if monetary transfers were allowed, we could probably do better in terms of efficiency. And my question is, can we, in the absence of money, can we create non-monetary instruments that would play the role of money or monetary transfers? And the answer is going to be yes. And how am I going to do that? I am going to introduce a new deferred acceptance mechanism, which we are going to call choice augmented deferred acceptance. It's going to be as before. Every student is going to be asked to submit ordinal preferences, and we would like to extract this information truthfully. But we will also ask them to send an auxiliary message, which we are going to call the target school. So which school are you targeting? And I'm going to tell you how this is going to work in a minute. We are also going to have two tiebreakers, a target tiebreaker and a regular tiebreaker. So how am I going to use this message along with those tiebreakers? This is how I'm going to do it. Within each, consider students that have the highest priority at school 1. Somehow we need to rank them in a strict order. Gale-Shapley does this randomly. We are also going to do this randomly, but we are going to favor students who target that school in tie-breaking. So within that priority group, we are going to rank students who target that school at the top, and below them we are going to rank students who do not target that school. And within each group, we are going to use the target and regular lotteries to break ties. Yes?
Can a student only target one school? Can a student target only one school?
In this mechanism, yes, but you can imagine targeting multiple schools or more elaborate message spaces. And if I have time, I'm going to touch on the issue. And actually, one of the lessons is actually keeping it simple works better in terms of efficiency. So students who pick that target school, that school as target, are going to be ranked higher, and the ties are going to be broken according to the target tiebreaker. And other students within that priority group are going to be ranked, and they are going to be ranked according to the regular tiebreaker. And then we are going to run the default acceptance. So here is a simple example. Students 1, 2, 3, 4, 5, schools A, B, and no priorities. Question? Yes?
So,
Go ahead.
so you have two lotteries for preferences. One you call the target tiebreaker, and the other you call the regular
Yeah.
tiebreaker.
That's kind of for technical reasons, actually. It makes the proofs easier. We started with a single lottery at the beginning, but it turns out that two lotteries are easier to deal with in the proofs.
Do you have, do you know that one of them will work better than the other, or?
Well, I think two tiebreakers would work better because I'm going to talk about this later. Because if you get a single lottery number, and if that lottery number turns out to be bad, you're going to get a bad luck at your target school and at all other schools. With that two lottery numbers, at least you're going to get a new life. If your target lottery turns out to be bad, you're going to get a second chance at the regular schools. At schools that you do not target. Yes.
So on your previous slides, you was always talking about schools have priorities and students have preferences. So you're right on your slide, on the slide before. Now you say students also have priorities. So you mean preferences in that sense?
Students have preferences, but schools are going to have no priorities in that example.
On your previous slide, if you go one slide back, rank students with each priority and differences. Each priority, so it's preferences.
Ranks within each priority in difference. Yes,
Yes,
schools might have
the schools
priorities. Yeah,
yeah.
yeah. Remember, consider the highest ranked students. Those might be the students who have siblings and who live within the walk zone of a school. There might be 20 such students. And 5 of them might actually target the school.
Okay, does the student have an incentive to put a school as his target, which is not his first preference?
Yes, yes, and we are going to see that actually. Yeah, definitely. So here is a simple example. 1, 3, and 4 target A, 2 and 5 target B, and here are the target lottery numbers. 3 has the best lottery number, best target and regular lottery number. The second best target lottery number is belongs to 5, and so on. So how do schools rank? School A. Remember, school A is indifferent between all students, right? The students have equal priority at that school. So those who target that school, which is 1, 3, and 4, are going to be ranked higher, and the tie between them is going to be broken according to this target lottery, 3, 1, 4. And the remaining students are going to be ranked next, and they are going to be ranked according to this regular lottery number. And school B is going to do the same, and we are going to run the default acceptance. So what is this good for? Well, one thing we can show in the finite economy, CADA is stable with respect to preferences and priorities. And actually, it is strategy proof with respect to ordinal preferences. What do I mean by this? I mean, given any strategy for myself, which is an ordinal ranking of schools and a target school, I can always do at least as well by ranking my schools in my true preference order and targeting the same school or some other school. So in that sense, there is no incentive to manipulate the ordinal rankings. And the gaming aspect of the mechanism.
The choice of the target school is also a dominant strategy?
No, no. The gaming aspect of CADA is limited to this target strategy. And that is where actually the sum of the cardinal information is going to be transmitted to the system. Yeah. More importantly, suppose people cannot play their Nash equilibrium. They play some according to some targeting behavior. Regardless of what targeting behavior we get, there's actually no individual rational assignment that every student strictly prefers over the CADA assignment. In a sense, choice augmented default acceptance is also optimizing student welfare on and off the equilibrium path. Yeah.
What does it mean to truthfully report my target school?
No, truthfully report target, truthfully not target school. Do I mention?
No, strategy proof with respect to students' ordinal preferences. So you mean only truthfully report my strict preferences?
Yes, only ordinal preferences.
But as a parent, how do I choose my target school?
And that is the tricky part, right? It is not simple. And so you are going to optimize, and I'm going to show you an example for that. Even if you do not play your optimal strategy, the CADA is still going to produce something that's going to be ordinally efficient. Efficient with respect to ordinal preferences. Now, here's the example again. In that example, there are no priorities. So every allocation is going to be ex post efficient. Everybody likes school 1, then school 2, then school 3. And default acceptance allocates schools with equal priority, and that's what they are going to get. Under CADA, what's going to happen? Each student is going to target one of those schools. There's no point of targeting your last choice. You are going to target either school 1 and school 2. If you are student 1 or 2, you would prefer to target school 1 because it's important for you to get into your first choice. If you are student 3, you have a reasonable second choice. If you target that school, you are going to be favored in tie breaking, and you are going to ensure assignment to that school. And in the unique equilibrium of that CADA game, in this example, actually student 1 and 2 are going to target S1, and 2 is going to target S2. And they are also going to submit their ordinal rankings truthfully. And that is going to produce higher expected payoffs for students under CADA. Yes?
You are seeing perfect information in CADA.
Mm-hmm.
Like
Correct, yes. Uh-huh.
How
Yes.
can 3 know that?
Hmm?
It's still not clear. How can number 3 know that he should target this 2?
If this is a complete information game, if 3 knows,
We're trying to know the other people.
yeah, that's a really that's a very tough assumption. I agree with that. And and I'm going to generalize that. I'm going to generalize this in a large economy where that kind of information asymmetry disappears. But the reason why I do it is not because I like the assumption, but because this is as close as I can get in terms of a tractable result. Yes. I'm also going to show you some simulation results under incomplete information.
You didn't try to apply it.
No, not yet. Yes.
If you had to give the parents an advice how to standardize the private school, would you similar advice to like you would give in Boston?
Not well.
So that you would say, okay, if you have a reasonable second, third choice, or whatever, then you might just take as a target to just get sure that at least you might get this. But if you are like really wanting to, for example, first choice, which would be your target?
There is an easy way of implementing that through a dynamic mechanism. And so ranking of schools, they can submit the ranking of schools truthfully without fear. They'll also target a school. You could actually reveal this information publicly and let people to update their targets by assessing the risks that they are facing. And one can show that this dynamic implementation, when it converges to a efficient, some sense of efficient allocation, which I'm going to tell about. Yes.
In a world where you actually have priorities in like this example, would the targeting actually go across priority class, or is it only within the same priority class that you can get the higher priority?
You could think of more sophisticated mechanisms with such elaborate messages, but in this case, you are only targeting a school.
Yeah, but like if someone else has a priority because he's still the one,
Yes.
then you get
No.
over him.
No.
So it doesn't solve the like neighborhood.
Correct.
priority issue.
Correct. By targeting a school, I do not, I cannot override students' priorities. I can only favor myself within my own priority group. So here is the model with a continuum of students. There are at least 2 schools, each with a unit mass. Students are going to have cardinal valuations, which are going to be drawn from this set. And we are going to have some regularity conditions. And schools, again, we are going to assume no priorities. But that's, again, I'm going to show, hopefully, if I have time, I'm going to show some simulation results with priorities. And this model actually can be justified as the limit of a sequence of large finite economies. Now, a random assignment is going to be a probability distribution over schools. That is the probability of being assigned to school 1, probability of being assigned to school 2, and so on. A random allocation is going to determine a random assignment for each student. That is student V, this is the valuation of student. And he's going to be assigned school 1 with this probability, school N with this probability. And I'm going to have this standard notion. I'm going to say that an allocation phi tilde, weakly Pareto dominates an allocation phi if every student's expected utility under phi tilde is at least as large as his expected utility under phi. And if a positive measure of students have a higher expected utility under phi tilde, in addition to that, I'm going to say that phi tilde Pareto dominates phi. That is the standard definition of Pareto optimality. And allocation is Pareto optimal. If there's no allocation, that Pareto dominates it. But we know that that's actually difficult to achieve in a strategy proof way. Let me skip that one and let me introduce a new notion of efficiency. In finite models, I already know that I cannot allocate all schools in a symmetric and Pareto efficient and strategy proof way. That is, there is no mechanism that is dominant strategy incentive compatible for students. That is Pareto efficient. That also assigns schools to students with equal probability, to students with the same messages. So given that, then I am going to relax my efficiency notion. So since I cannot achieve the efficient allocation of full set of schools, I am going to try to allocate a subset of schools efficiently. So take a subset of schools and consider an assignment X. Remember, that is the probability of getting school 1, probability of getting school 2, and so on. I am going to consider a within K reassignment. What is a within K reassignment? Within K reassignment fixes the probability of being assigned to any school outside of K and changes the probability of assignment to schools within K. And I'm going to do this for all students. I'm going to try to reallocate the probability of assignment to schools within K among all students. And I'm going to call phi tilde a within K reallocation of phi if every student's assignment is a within K reassignment. Now, so in words, a within K reallocation of phi actually involves possible trading of students' assignment probabilities over schools within K. Now, what is this good for? I am going to give a new Pareto optimality definition. I'm going to say that an allocation is Pareto optimal within K if I cannot reallocate those probabilities within K in a way that everybody gets better off. Weakly better off and some strictly better off. And let me skip this one. So I'm going to talk about three types of mechanisms. A deferred acceptance mechanism that actually uses a single lottery to break ties at every school. Deferred acceptance mechanism that uses school-specific lotteries. Every school runs its own lottery. And the CADA mechanism. So when we compare this, I'm going to get back to this example later. I'm also going to give you a couple of definitions quickly. A school is popular if the number of seats at that school is smaller than the number of students ranking that school as their first choice. And a school is worst if getting into that school is guaranteed. If I rank that school in my choice list, and if I don't get a better school, I'm going to get that school for sure under deferred acceptance. There always exists such a worst school. And a school is oversubscribed if the number of seats at that school is less than the number of students picking it as target in CADA. That is an equilibrium notion, right? It's going to be determined in equilibrium. But this is not. In general, the set of popular schools is a subset of oversubscribed schools. So what do we have? With the multiple tie breaking, we can allocate at most 2 schools Pareto efficiently. And one of them has to be one of those worst schools. That's not a big achievement. With the deferred acceptance with single tie breaking, we can allocate at most 2 schools Pareto efficiently. If I put a third school within the set, I cannot guarantee Pareto efficiency within that set of 3 schools. With CADA, first of all, CADA equilibrium exists in this continuum economy. And it is also Pareto efficient within the set of oversubscribed schools. And remember that that is an equilibrium. This is going to be determined in equilibrium. And actually, it may be the case that the set of oversubscribed schools is actually equal to the set of all schools but one, the worst school. Then in that case, CADA is going to be fully efficient. And if you are not comfortable with this equilibrium concept, CADA is also Pareto efficient within popular schools. So pick the popular schools. CADA is always going to allocate popular schools Pareto efficiently. Deferred acceptance with single tie breaking, which is the better option of the two, is not going to achieve that efficiency result. Now, the proof is really similar to the proof of the first welfare theorem. Suppose, consider this maximization problem. I am student I am trying to maximize my expected utility. This is my evaluation. This is my probability of getting into school I. That I am student V. Subject to what? Subject to, these are the probabilities that I would get under my Kada equilibrium. I'm going to sell them in the market, and I'm going to buy new shares. And I'm going to do it only over subscribed schools. And we can show that actually this is a more constrained problem than the Kada game. And actually any X that is feasible for this problem can be generated as a within the any assignment that's feasible here can be achieved within the Kada game. I have a strategy in the Kada game that's going to replicate those X's. Given that my equilibrium strategy solves a more relaxed problem, my equilibrium strategy would solve this one as well. The solution to this problem would be phi star. Once I obtain this, I use the standard techniques of the first welfare, the proof of the first welfare theorem, and show that allocation within oversubscribed, within the set of oversubscribed schools is going to be Pareto efficient. Now, the reason why we achieve efficiency within oversubscribed schools is because of relative congestion. Relative congestion, since there are more students that target as an oversubscribed school than the available seats at that school, the popularity of the school serves as a pricing mechanism. The more students targeting it, the less likely for me to get into that school. So the higher the price of the school is. And it is, in Kada, it is, efficiency is restricted to oversubscribed schools because there's no pricing system that regulates admissions to undersubscribed schools. Regardless of how many students target a school, an undersubscribed school, I would guarantee to get into that school if I target that school. And ex-post efficiency is also achieved. And in the remaining couple of minutes, let me show you a couple of simulations. So 100 students, 5 schools, and 20 seats. This is going to be an incomplete information game. No, actually, this is going to be a complete information game. I'm going to introduce priorities here. So a student I's preference for school J is going to have 2 components: a school fixed effect plus a student specific utility term. And if alpha is equal to 1, everybody is going to rank schools the same way. If alpha is equal to 0, the preferences are going to be drawn idiosyncratically and identically from the same distribution. Alpha, in a sense, measures the correlation among preferences. And once we do that, as alpha goes from 0 to 1, actually, the correlation among preferences increase. And what we do is we compute the first best in any economy. And then we compute the average utilities generated by Kada, by deferred acceptance with single tie breaking and deferred acceptance with multiple tie breaking. We see that actually as if there's no correlation among preferences, pretty much everybody gets into their first choice because it's being determined randomly. If preferences are completely correlated, then it doesn't matter who gets what. So they continue to perform equally as well. But within the middle range of correlation, actually, Kada outperforms both deferred acceptance with single tie breaking and deferred acceptance with multiple tie breaking. And the reason why it outperforms those 2 schools is not because it assigns more students to their first choices. Actually, you look at the percentage of students who get their first choices. Under Kada and deferred acceptance with single tie breaking, they are almost the same everywhere. But it's not that, it's who gets into their first choice. Here in that graph, we compare the utilities of those students who get their kth choice. For the students who get their first choice, CADA improves students' expected utilities slightly. But for those students who get into their second choice under CADA, it improves those students' expected utilities significantly. So CADA helps students with a better second option to go after those schools. That is how the simple signaling device actually plays a role in reallocating students. I think I am running out of time. It's a good time to stop, but I could continue after during the break.